All right, AP 20.5. Let's talk about how this delta G and E are going to come together. So we have our learning objective. Let me make my page a little bigger for us going blind people because of staring at computers for 14 months. All right, so 20.5, free energy and redox reactions. So explain whether a thermochemical cell, okay, so voltaic cell, is thermodynamically favored. So we're looking for that delta G and E to be opposite signs based on the standard cell potential and the half reactions within them. Okay, so based off that cell potential and those half reactions, okay, because the electrons are going to be a big key to this calculation. So delta G, standard state, Gibbs free energy, that is the only one you could be looking at for spontaneous or not, is proportional to the negative of the E cell for those redox reactions. Okay, so what they're telling you is that this delta G, if it is going to be thermodynamically favored, we already know delta G should be negative. Okay, is proportional to the negative of the cell potential. And our standard, sorry, not degree, I'm so used to writing little triangles. Our E cell potential, remember that's what it's called, E cell potential, has to be positive. Okay, that is the only way it'll be thermodynamically favored. The E cell with the positive, the cell with the positive E cell value, cell potential, involves a thermodynamically favored reaction, and a cell with a negative E is obviously thermodynamically unfavored. So in order for a voltaic cell to actually perform on its own, it has to be E cell of positive. And we get our next equation, delta G equals negative NFE. So on our equation sheet, I wanted to show you where they're listed. We just got done practicing delta G negative RT natural log K in chapter 19. We're getting ready to do this one, negative NFE, and then 20.6, this guy's going to pop up, and then the very last section, this one. So we'll get to that. So you do have some help right there. So a standard electrochemical process, we know that our E cell, and we need to keep these values in reduction form, in standard reduction form, is the cathode minus the anode. Don't flip any numbers, okay? Just because the equation gets flipped, do not flip any numbers. Just take the reduction numbers, and just subtract. Okay? As I told you, Fairbrother, he has his own way, and if it makes sense to you that way, great, do it. Okay? I'm just not a fan of that way because it confuses students. So when you do this equation, the cathode minus anode, okay? So those E reduction values, don't flip any signs, okay, when you do the cathode minus anode. If we get this E reduction value spontaneous, and actually this should say E cells, not reduction, indicate a thermodynamically favored process, and that's the only way a voltaic cell will actually work. So like your batteries will only work if they have a positive charge. Your E cell indicates, if it's negative, indicates that it's not thermodynamically favored. So if I have this right here, consider the reaction of nickel with silver, and I get nickel, and I want you to see the nickel solid going to the nickel plus 2, and that means, okay, 2 electrons, he was oxidized, okay, oxidation's occurring there, and my silver, Ag, now remember, do not bring these coefficients down when you're doing the half reactions. Those coefficients came about when they balanced the equation. Okay, so these are my 2 half reactions, and this is where reduction occurred. When I bring these 2 equations together, I need this equation right here, I need these to say 2 electrons. So if I multiply everything by 2, then that becomes my 2 electrons, my 2 silver ions, my 2 silver solids. And that's how I cancel them out. So when I bring this together, This is where this guy comes from. So when you're doing the half reactions, ladies and gentlemen, do not bring these coefficients down with it because they got there after you brought the two half cells together. So when you get the values for silver, you just bring up those values, 0.80 volts, and then the nickel, the N plus and the N, okay, you find those two half reactions and negative, and now I know that my E cell is positive and definitely thermodynamically favored because it is positive. Okay, remember AP will give you a chart. It'll be a very tiny chart, so you won't have to go through the whole big mess of the giant appendix that we have. So real quick, ladies and gentlemen, when you're looking for these values, so right here, here's our silver one, okay, right there. Remember, they're in standard reduction form. So that silver right there is 0.80, okay, and we look at our notes. We have silver as 0.80, and then we look at the nickel one from the ion plus 2 to the solid. So if I go on my chart, it looks like the nickel one's right there. Okay, now the values that I have on my paper is from the appendix in the book. Okay, so this right here going to the solid is -0.25, and I have 0.28. Okay, it's only because I didn't have this chart with me. So we're going to go right here, 0.25, according to our values that AP would give us. And then when we subtract that, let's get some beautiful calculators because it is too early for me to do math in my head. So 0.80 minus a negative 0.25, and we're going to get 105. Okay, and regardless, ladies and gentlemen, it's still thermodynamically favored. Okay. How do we use E to confirm that delta G is going to be negative when we want him to be thermodynamically favored? Well, we have this equation where it relates EMF, and remember EMF, electromotive force, which is the same thing as cell potential. Okay, remember we call cell potential many different things. Okay, so EMF, electromotive force, and delta G. Here's our equation right here. If it is in standard state, then we have the little degree signs, and if it's not, well then it's not. Okay, and basically that means either temperature was either not 298, or maybe pressure was not 1 atm. And remember, concentration maybe was not 1 molarity, and that's coming in the nasty next video. Okay, I ain't gonna lie, it's gonna get a little nasty in 20.6. Okay, delta G gives free energy, the only one that you can mention that thermodynamically favored. But now delta E you can also too. Constant temperature, constant pressure. Now we got N. Now this is going to be a big one for you. It's not just moles. It's moles of electrons. It's the moles that were canceled out. Okay, so when you are balancing your half reactions, it's the electrons that are canceled. Okay, because one of them has 1 electron and the other one has 2 electrons. It's a 2 because you needed 2 electrons to cancel out both half reactions. So the electrons that were canceled. F is Faraday's constant, and Faraday's constant, he is basically the father of electricity. That's why sometimes in my videos I kept saying Faraday instead of Farabra. Faraday's constant, okay, and his value is right there. Okay, 1 Faraday equals 96,485 coulombs over moles. And remember, what is a coulomb? So if I rearrange this equation right here, 1 volt equals a joule over coulombs. So if I want a coulomb, well, these two just kind of just play swappy-doo, and we get our joule over volts. So if I insert this coulombs right here, this is where I get those units. Okay, and this is the one we're going to be using. So joule over volt, and then the mole doesn't disappear. He's still right there. Okay, so I just basically inserted that C. Now on our equation sheet, I don't know if they still have it there, but let's take a look. Oh, look right there. but it says right here, coulombs per mole. So they give you the big C over mole, but they do give you a hint, a volt, joule over coulomb. So you get some love there. You definitely do. So they give you this one on the equation sheet, but they do also tell you this, okay, which is also nice. So make sure you know how a big C can get converted to help you with the joules over the V. And we already know that E is our electromotive cell, okay? So we got everything we need. It's a simple equation. It's a plug and chug. And as long as we know that moles is always positive, we know Faraday, being a constant, is always positive. If delta G is less than 0, so negative, and our E cell is positive, we know that this electrochemical cell, aka voltaic cell, will be thermodynamically favored. Okay. Now, real quick wise, I cut and paste some examples, so we're going to do these ones. And I know you should have some space in your notes. You can add it there. If not, just do it on a piece of paper. Okay. So here we go. Let me get set up myself. And oops. I'm going to show you a couple things in the textbook too. All right, so we have this reaction, and I want to find delta G, and I want to solve for K, because we do need that practice back from chapter 19. Well, the first thing is that they don't mention, it says using the standard reduction potentials in table 20.1. Table 20.1, that's our appendix that's in the back of the book. We also need to calculate E cell. Because in order for us to use this equation above, ladies and gentlemen, we're going to solve for delta G, but I need what E cell is. I need that cathode minus anode part. So if I take this equation, let me find my two half reactions. I got my silver solid, and it goes to my silver plus 1, and I have my 1 electron sitting over here, aqueous. And we have that value. And it was, what was it right here? It's 0.80, okay? So I'm going to label that E red, degree sign, 0.80, okay? Now, was this oxidized or reduced? This is where oxidation occurred. And because that's oxidation, I know that's my anode, okay? Now, this other half reaction, you're not used to. This guy right here. In our appendix, and I'm going to show you in the appendix in the back of the book. I just did not include it in here. I know it's on page 1064, so I can show you. We have this one, O2 gas, and I'm not bringing those coefficients down, plus H plus, aqueous, gives me water. Okay, now where is that half reaction? And let me get the page. All right, so let me bring, in the back of the book, remember when we had our, let me scroll to the page, we had our Ka values, we had our thermodynamic values, okay, which I believe was appendix, let me go, appendix C was our Mama Jamma one, and then we had our Ka values. And the next appendix in back of that is the appendix E, standard potentials. Now these are all the big half cells, not just a simple element solid broke up to the ions, or the ions went into the solid. These are even more complex. Okay, now AP has to give you these. Okay, there's no way you can figure these out from anything. So the one we're looking for is the one that has O2 gas with H ions, some electrons somewhere, and then water right here. So if I go through here, and I'm looking for, remember I want O2, and I don't see any O2 or H2 up here because it's alphabetical, but I do see something over here. So I see 3 equations right there with O2, and I want the one with H plus, so it could be either this one or it could be this 2H plus or the 4H plus. But this one forms hydrogen peroxide. I'm not trying to find hydrogen peroxide. I'm trying to form water. This is my half reaction right here that I want. So the O2 plus 4H plus, 4 electrons, gives me 2 waters. and that right there. So let me kind of put this to the side so I can write it down. Let me make you come over here so I can see it. All right, so I got my O2 gas, and right here it says 4H plus, and it does say 4 electrons. I'm just going to write those over there. And my 2 waters, and it did say an E red standard state. I believe it said 1.23. Let me double check. 1.23, yep, 1.23, okay? So remember when you're doing the AP dailies, you're seeing how they give you like a small chart, okay? Trust me, it's a very small chart. You're not gonna have a giant appendix. But remember these charts, they're gonna give it to you in reduction form. So even though this equation right here, see where the electrons are on the reactant side, that means this is where reduction occurred. And somewhere in here is my cathode, okay? So I have both my E red numbers, and if I bring these together so I can show you how this balanced equation came about, I have 4 electrons here, but I only have 1 over here. So that means this equation right up here, I'm going to have to multiply by 4. I'm just telling AP what I'm doing. And by multiplying by 4, I'm just going to put 4's in front. And now that's how my 4 electrons go away. So when I bring these two together, I got my silver, I got my oxygen gas, my 4 hydrogens, and I got my 2 waters, and I got my 4 Ag+. And I want to make sure my equation's balanced because we are good AP students and we're going to make sure everything's balanced. My 4 silvers on both sides, my 4 hydrogens both sides, my 2 oxygens, and my charges. I got 4 H+ here, I got 4 Ag+ over there, and everybody else is neutral, okay? But just because I multiplied the half cell by 4, we do not multiply by 4, okay? It doesn't matter what you do to this half cell, that E cell will always still measure that value. If you half those coefficients, if you double them, it don't matter. That E cell is going to be whatever it is. So remember in the notes it says the coefficients changing, there is no effect to the E reduction value. No effect on what you do to those coefficients, okay? So I have my 2 values. I know who my anode and cathode is. So I'm going to take my E cell, because I can't find delta G unless I know what E cell is. And I'm going to take, bad triangle, no triangles. We're going to take our E red, and I'm going to put the word cathode, minus my E red and anode. Make sure you guys have calculators because you know Rodriguez, sometimes her fingers go a little crazy. And I know my cathode was this hydrogen equation. So I have this 1.23 volts minus my anode was the silver, 0.80 volts. Very simple, plug and chug. Let's don't screw up on those sig figs. So 1.23 minus 0.8 and 2 sig figs in back, so about 0.43 volts. Okay, so big V, and my E cell is 0.43 volts. Now we're going to solve for delta G. As I said, it's a very simple equation. Negative NF E, the N, as you saw right up here, N is number of electrons transferred, okay? I had 4 electrons here, but I had 1 over here. To cancel these out, I had to multiply this equation by 4. That's the moles of electrons. So for this N, you put 4 moles, okay? So it's the number of electrons. I got my Faraday's constant, and Faraday's constant, 96485. And remember, we need this one, the joules volts, because in the end, ladies and gentlemen, I don't need moles for delta G. Because remember, delta G usually has units of kilojoules per mole or just kilojoules. Okay, sometimes it'll have both. Most of the time, it just has that kilojoules per mole. So J volt right there. And it doesn't matter which one goes in which order. And then my E cell was 0.43 volts. Okay. Now, because delta G usually has this unit instead, I'm going to take this word mole out because it's not needed, because I want that mole to stay there. I want to make sure I have my proper units, because now delta G for AP, back in the day, kilojoules was just fine. But they want your units to be kilojoules per mole. So always pay attention to whatever units AP says in their questions. That's like the one thing I'd be circling, is when I'm reading that question and it says calculate delta G in kilojoules per mole, bam, circle that guy. Because you want to make sure you do the units they want. There is no love if you do not put it in the correct units. Okay. Now I'm going to make a little observation here. My E cell was positive, 0.43. That means this is definitely thermodynamically favored, definitely spontaneous. So when I do my delta G, this answer better be negative. Okay. And it looks like it's going to be, because this negative in the equation is still negative. So I'm going to take my -4, multiply by 96485.43. And you know you're going to get big numbers. If you got to go scientific notation, that's fine. Now right here, ladies and gentlemen, this 4 moles, that's a constant. Okay, that has nothing to do with sig figs. Just like Faraday's is a constant too, but I do have 5 sig figs versus 2. Our answer needs to only have that 2 sig figs. Okay, so right here, we're not looking at sig figs. Okay, for those 4 moles of electrons. So I get a big number, negative 165954. So we're going to go 2 sig figs and definitely some scientific notation. You could even say negative 160,000, or but there is a 5 and there is a 9 after the 5. So actually I'm going to round that 6 to a 7. There you go. So if you want to put this in scientific notation instead, 1.7 to the 5th, that's fine. And the only thing that cancels is the volts. And I got my joules per mole. Okay. But you know they want kilojoules per mole. Okay. So if I take this number, do a little King Henry, joules. Remember, joules is here, kilo's over here. 3 places to go to kilo. Then I'm going to get negative 170. Okay. I'm looking at this number right there. Negative 170 kJ per mole. And now I definitely know thermodynamically favored and thermodynamically favored. They have to be opposites of signs. Okay. So there's my delta G. As I told you, simple plug and chug. Okay. The last one is K. Do we remember how to plug in for K? So remember for K, and back in chapter 19, so reviewing of chapter 19, we have our K is E negative delta G standard state over RT. Okay, so remember that equation. And I believe he's on your, let's check out that equation sheet again. Yep, see, he's right there. So right here on our equation sheet, they list it like this. Delta G, and they have it right there, negative RT natural log, negative RT natural log of K. It's right there, okay? But what scares me, ladies and gentlemen, is when you start to plug this in and then you get to the natural log of K and you box that answer. No, no, no. Do a little review here. Delta G, if I want to bring this part over to the other side, then it's divided by negative RT, and I get natural log of K. That's not the answer. You got to get rid of the natural log. And if you notice your natural log button, natural log, there's an E right above it. So what you have to do is you have to take the E to both sides, and that's how the natural log cancels out. And now you have K. All right, just showing you how to derive it. Okay, like Fisher says, derive it or drive it, or one of those things, drive or derive, I don't know, one of those. All right, so delta, so we have our K, and we're going to go E negative. Now right here, ladies and gentlemen, we have our delta G, 170 kJ per mole. Now be very careful with that R. Remember R, do a little review over here, R 8.314, J mole K, but I can't put that number under here because they won't cancel, okay? So move that joules over, so 0.008314 kJ mole K. And this is where, ladies and gentlemen, it scares me because time, and you're sweating during the test, and you're trying to hurry and answer every single problem. You gotta check the ones you know. If you're gonna solve a problem, you gotta make sure you're doing everything correct. Because even if you do the whole test, but if you didn't check to make sure you had the right units and what they canceled or not, then what was the point of that by answering every question? Okay, so make sure the ones you can answer in that time frame, that it's right, and you're sure that it's right. So kJ per mole, and then multiply 298K. So bye-bye K, mole's gone, KJ's gone. It doesn't matter because K has no units anyways. So when I plug this in, and I'm going to make sure I plug it in joule this time. I'm going to make sure. So negative 170 divided by 0.008314, and I'm going to divide again by 298. So last time, Jules, you made a boo-boo, Rodriguez. Never. It's my calculator. I blame my calculator all the time. So right here, I get a negative. It's about 68.615, blah, blah, blah. You don't have to write that. I'm just showing what value I got. And now I'm going to take e to that. Now, you don't have to clear your calculator, ladies and gentlemen. Just keep it flowing. Keep it going. So negative. And I get big value. K is, now I get 1 point, what are we doing? Two sig figs. So 1.6 times 10 to the negative 30. Okay. Now my book, because they have, let's see. Yeah, because when they get to this part right here, they use 2 sig figs instead of all the value. Instead of using the whole calculator, they use e to the negative 69 right there. So they get this value instead, about 9 point, I think they said 1 times 10 to the negative 29. So it depends, ladies and gentlemen, on how you plug it in. Now that's a huge difference. That's literally a factor of 10 that you're off. And that's okay, because AP, remember I told you back when we were doing natural logs and logs back in kinetics, you get a bigger range that you can be off. So if you show them this, ladies and gentlemen, then just use the 2 sig figs, okay? But if you're going to use more numbers, then you got to show them like exactly what you're doing, okay? So that's the two